In today's video, we're going to continue our discussion of enols and enolates as nucleophiles with the Aldol and Claisen reactions. In the Aldol reaction, the starting material is aldehyde or a ketone, and the aldehyde and ketone will act both as the nucleophile and the electrophile. While this reaction can occur in both acidic and basic conditions, we're going to focus on the reaction under basic conditions. So here we have acetone with a base, and in the first step, we are going to generate the enolate by deprotonating an alpha hydrogen. Acetone only has one type of alpha hydrogen, and so it doesn't matter which one I choose. I could pick from this carbon or this carbon, but I've drawn M1, and so we're going to deprotonate that, kick these electrons up and that over to generate the enolate. Now remember that enolates are resonance stabilized, so there is another less important resonance structure to this molecule or this intermediate, and we can draw it down here where the negative charge is centered on carbon rather than oxygen. Once we've generated the enolate, we're going to use a second ketone or molecule of acetone as the electrophile. And so just like other reactions with enolates, the lone pair on oxygen kicks down and kicks these electrons out, and the carbonyl carbon is electrophilic, and so it's going to attack the carbonyl carbon here. So we reform the carbonyl and we form a new bond to the alpha carbon of the other ketone, which has two methyl groups hanging off of it, like this. And in the final step of the Aldol reaction, the water molecule that we just formed gets deprotonated to regenerate the base and form the final product, which is a beta hydroxy ketone. So the hydroxy group is on the beta carbon, and so it's a beta hydroxy ketone. And I've color coded this so that you can see where these three carbons and that oxygen came from the initial enolate molecule, and the green part of the molecule is coming from what acted as the electrophile. If you compare the reactivities of aldehydes and ketones, aldehydes are in general more reactive than ketones. The Aldol reaction gives a beta hydroxy ketone as the product. Here's an example of the product that we just formed on the last slide. But beta hydroxyketones can undergo dehydration reactions under acidic or basic conditions. And since the aldol reaction can be run under basic or acidic conditions, oftentimes you don't get a beta hydroxyketone as a product, but you get an alpha beta unsaturated ketone. And so let's take a look at that mechanism. Under basic conditions, it does require a little bit of heat. And so if you run the aldol at cold reaction temperatures, sometimes you can have it stop at the beta hydroxyketone. But if you add a little bit of heat, we can deprotonate the alpha hydrogen and form an enolate again. And then that enolate can undergo an elimination where these electrons kick down, these electrons kick over, and kick this OH off. And I know that OH is not typically used as a leaving group, but under strongly basic conditions, OH can leave. And what's important about this part of the reaction is that the aldol reaction is an equilibrium reaction, but this dehydration is unidirectional. And so this is not under equilibrium, but will be formed and stop at that alpha beta unsaturated ketone. Beta hydroxyketones can also dehydrate under acidic conditions. And so in the first step, we're going to tautomerize the ketone by protonating it. Remember that tautomerization is reversible, and so we're going to draw this as an equilibrium. And in the second step of tautomerization, we deprotonate the alpha hydrogen to generate the enol. Here. Then we're going to protonate the beta hydroxy group to create a good leaving group. We can take these electrons and kick down. These electrons will kick over and kick off water to give the protonated ketone. And in a final step, we can deprotonate the ketone. To give the alpha beta unsaturated ketone as the final product. Let's take a look at a couple of more examples of the aldol reaction. And I'll note that these two sets of conditions are slightly different, but I expect the final product of these two to be the alpha beta unsaturated ketone formed through the aldol reaction. And so if we're just predicting the products, I'm going to start out by drawing one of my aldehydes in this first example as it is. And this aldehyde is the one that would have acted as the nucleophile, and it's nucleophilic at the alpha carbon. And since aldehydes only have one alpha carbon, I don't have a choice. It's this one. And right below that alpha carbon, I'm going to draw a second starting material, and the aldehyde would have been here, but I'm actually going to get rid of that carbonyl oxygen. And in between the carbonyl carbon of the electrophile and the alpha carbon of the nucleophile is going to be a double bond. And so this is the alpha beta unsaturated carbonyl, or aldehyde in this case, that would have formed, or that would form under these Aldol conditions, where this blue part of the molecule was one of the aldehydes, and this is the one that acted as the nucleophile. And this green part comes from the other aldehyde, and it's the one that would have acted as the electrophile. If we wanted to draw the mechanism of this, we'll draw that completely one more time. And so the first step, again, is generating the enolate. Which is going to react with a second aldehyde. So we're going to kick these electrons back down, kick this over like so. That forms this molecule. We have recently generated water, and so we're going to protonate this O minus. To form the beta hydroxyketone. We're then going to dehydrate that by grabbing that alpha hydrogen and forming an enolate. It's getting a little crowded here, but I think we can fit it. And then finally, we're going to kick these electrons down, kick these electrons down, and kick that OH off. And that final step really is not an equilibrium like I'm drawing here. It is a forward reaction only to form this as the final product. If we repeat the predict the products process again for this bottom one, I'm going to draw the cyclohexanone as is, and I'm going to designate that this is going to be my nucleophilic carbon. It could have been that one just as easy, but I'm going to designate that one. And then I'm going to draw another molecule of cyclohexanone without the carbonyl, and so I've just sort of replicated the cyclohexene part right here. But this carbon is the one that used to be the carbonyl, and I'm going to connect the alpha carbon and the carbonyl carbon with a double bond. And so this is the final product of this reaction at the bottom. So far we've looked at the Aldol reactions where the electrophile and the nucleophile are the same molecule. You might imagine that there could be a scenario in which you have a mixed or cross-Aldol reaction in which the nucleophile and the electrophile are different ketones or different carbonyl compounds. And this can be quite useful, but it can also lead to a disastrous mixture of products if you're not careful. So in this first example here, the struggle that we have is there are two types of enolizable hydrogens. We've got acetone with cyclopentanone, and they both have enolizable hydrogens. So hydrogen on acetone there is enolizable, and it's the same kind of hydrogen as that one, but I'll draw it in too. But the hydrogen on cyclopentanone is also enolizable, and so we could deprotonate either one of those things, and they're going to lead to different products. So if I choose to generate the acetone enolate, that's going to look like this here. And that molecule or enolate could react with another acetone. And so if I draw acetone here, this is the nucleophilic carbon, and so I'm going to draw another molecule of acetone with the carbonyl carbon pointed towards it and connect them with a double bond. So that is one potential product, but that had it reacting with acetone. What if it reacted with cyclopentanone instead? And so we could form this product. And again, I've redrawn the cyclopentanone, but I've omitted the carbonyl, which would have been on that carbon. And I'm going to connect the alpha carbon of the nucleophile to the carbonyl carbon of the electrophile with a double bond. And so enolizing or forming an enolate out of acetone could lead to two potential products. But I could also enolize or form an enolate out of cyclopentanone. So this might also form. And in that case, again, my cyclopentanone this time can react with a molecule of acetone and form this alpha beta unsaturated ketone, or it could react with another molecule of cyclopentanone and form this alpha beta unsaturated ketone. And so if you start with two ketones that both have enolizable protons, you can have at least 4 potential products. And that assumes that the enolizable protons on the two molecules are the same, meaning that we have two symmetric ketones, so it could be even more problematic, given more complicated ketones. But if you were to set this up properly, you can do some interesting cross-aldol reactions that we'll take a look at in a second. In this example of a crossed or mixed aldol reaction, only one of our reagents has alpha hydrogens, and so there's only one type of enolizable proton. And in this example, it's on acetaldehyde right here. And so sodium hydroxide will deprotonate that to form this enolate here. Now, under normal reaction conditions, this enolate could react with another molecule of itself, acetaldehyde, or it could react with benzaldehyde. If we were to set this reaction up such that we have excess benzaldehyde, then we can ensure that it primarily reacts with only benzaldehyde. And so if you want to do a crossed aldol reaction with only one type of alpha hydrogen, adding excess of the molecule that doesn't have any alpha hydrogens can help ensure that you only form one product. And so the final product of this, we're going to draw acetaldehyde like so, and right under it, I'm going to put the carbonyl carbon of benzaldehyde and then redraw benzaldehyde here. And where there used to be a C double bond O on benzaldehyde, I'm going to make a carbon-carbon double bond to the alpha carbon of acetaldehyde to generate this alpha-beta unsaturated carbonyl as the final product. Now, it's possible that this could form both E and Z isomers, but the E isomer is more stable, and so we expect to see that as the major product. If you want to add or do a mixed aldol reaction where multiple types of enolizable protons exist, you can, rather than using sodium hydroxide that generates the enolate in an equilibrium, you can use a stronger base like LDA or lithium diisopropylamide. It's this molecule here. It's a very strong base, and so it will stoichiometrically generate the enolate from here. To give this. And so you do this before you ever add the second compound. And now we can add this aldehyde in a second reaction or a second step so that we generate this. And then we're adding water. And as long as we kept this reasonably cool and just added water in the second step, this could stop at the beta hydroxyketone. If, however, we used in step 2 either acid or base, we would expect this to generate the alpha beta unsaturated ketone instead, which would look like this, where this part of the molecule came from the aldehyde here, and this part of the molecule came from cyclohexanone here. The Claisen condensation is similar to the Aldol reaction, except you start with an ester instead of aldehyde or ketone. And the alpha hydrogen on an ester is slightly less acidic than the alpha hydrogen on an aldehyde and a ketone. And so it requires a little bit stronger of a base. And so instead of sodium hydroxide, we're going to use sodium ethoxide to deprotonate. And we're going to generate the enolate just like before in the first step. And so these electrons are going to attack the alpha hydrogen. This is going to kick over and up to generate this enolate. And then just like the aldol reaction, once you generate the enolate, a second molecule of the ester, in this case, is going to act as the electrophile. And so we're going to kick these electrons down. These electrons are coming over and kick that up. And so this first step was in equilibrium, and the second step is also in equilibrium. Let's keep our color coding the same. This is O minus. This is the ethyl group here. So this is where the Claisen condensation and the aldol reaction diverge. So just like other additions to esters, once you form this tetrahedral intermediate, the electrons on oxygen can kick back down and kick off the other oxygen, because the alkoxide in this case is a reasonably good leaving group. So it's only a good leaving group because we're already in strong base. That's and that leaves you with this. And that is actually going to wind up being the final product, but it goes through a couple of conversions first, because we just generated this OET minus, and this alpha hydrogen is very acidic because it's between two different carbonyl functional groups. It's going to get deprotonated. That's not where that arrow goes. Fix this molecule. That arrow goes to hydrogen. This goes up to form an enolate. And this is actually the first irreversible step in this reaction. And then in a second step, that's where it stops until you add acid, and we're adding HCl here. So in the second step, these electrons kick back down. That kicks over. And those those go there to generate the final product in this Claisen condensation, where this part came from the nucleophilic ester here, or the enolate, and the green part here is this part of the electrophilic ester here. This first irreversible step here, where we deprotonate the alpha hydrogen, is the second alpha hydrogen on this carbon that we've deprotonated. And so for the Claisen reaction to work, the starting ester must have 2 alpha hydrogens. The starting ester must have 2 alpha hydrogen atoms. Just like the Aldol reaction, we can do a mixed Claisen reaction where I use 2 different starting esters in this case. For the one shown here, only one of these esters has alpha hydrogens or enolizable hydrogens, and that's this molecule here. That one is going to wind up being our nucleophile, which means this other ester is going to wind up being the electrophile. Notice that we have set it up in excess. This is because once we generate the enolate from the other ester, we want to make sure it only attacks the other ester and doesn't do a Claisen with itself. When I'm predicting the products here, I'm going to use a slightly different algorithm. And so I am going to draw the electrophile without its leaving group here first. Just like that. There's going to be a bond from that carbonyl to the alpha carbon of the other ester. And so I'm going to draw the other ester up like this. And that other ester had 2 carbons hanging off of the alpha carbon. And so this is the alpha carbon, and it's got 2 carbons hanging off of it. It's never a bad idea to make sure to count your carbons at the end of this. And so this part is 6 carbons, 7, 8, 9, 10, 11, 12, 13. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 that should be incorporated into my product. If we wanted to draw the mechanism for this formation, the first thing we would do is pluck off an alpha hydrogen right there and form the enolate. Enolate, not the ketone. Enolate. And then this enolate is going to attack the electrophile. Like so. And just like other additions to esters, we first form a tetrahedral intermediate. like that. And then this kicks down and kicks that leaving group off to form this plus an OET minus, which initially is going to deprotonate here to form the enolate again. And actually, I drew that as an equilibrium, but it is not an equilibrium. This is a forward reaction only. And then that gets treated with HCl to form the final product, which was and I probably should have said this on the last slide, but I didn't. The product of a Claisen condensation is a 1,3-dicarbonyl. And so this carbonyl is on carbon 1, 2, and this one is on carbon 3 relative to that. So it's a 1,3-dicarbonyl. Similarly, we can also do a Claisen condensation with two molecules that have enolizable protons if we add them sequentially and use a really strong base like LDA. In this case, we're using acetone as our nucleophile, and so we're going to generate the enolate from acetone using LDA. Remember, LDA was a strong base, and we can generate the enolate like so. And the Claisen condensation typically uses two esters, but in mixed Claisens, the nucleophile could be an aldehyde or a ketone, and the electrophile needs to be an ester. And so in this case, the ester is here, and we're going to add that slowly after we have generated the enolate. And so I am going to draw the ester without the leaving group. So I've left off the OET. And then right beside it, I'm going to draw the nucleophilic portion, which was acetone, which we formed the enolate out of. And then the alpha carbon, or the nucleophilic carbon, is directly attached to the carbonyl carbon of the ester. And so that makes the final product a 1,3-diketone, where this yellow part of the molecule comes from this ester minus the alkoxy leaving group, and the blue part of the molecule comes from acetone. That's going to wrap up our discussion on the Aldol and Claisen reactions.